Thus far, we have been studying stereo, which is a passive multi-directional technique. Now we move to the other side. We will see our first active method, and that means now illumination is involved, and we do something special to the illumination. We project a pattern. And the method we will start with is this active multi-directional technique, line scattering. Now, looking at stereo, the hard problem was finding the corresponding points. So here's now the idea. Suppose I replace one of the two cameras in my stereo system by a projector. For instance, a laser pointer. So I have my laser pointer and a camera. These two things. My laser projects into the scene, and there will be this bright laser spot somewhere that I don't find difficult to find in my image. Now, if I know the equation of my laser line, I can also take the projection equation of my camera, where I see that laser point, and where the two intersect must be the point in 3D. That must be the point where my laser light is hitting some surface. That gives me 1 point. Now, of course, 1 point typically won't be enough. So what we can do though is to start scanning. So rather than having the 1 point with our laser line, we will start to scan all over the scene. So we will move this laser line over the scene, and point by point I can make my 3D reconstruction. So that was the idea of the initial laser scanners. And the problem is that this scanning takes a lot of time. It may sound like innocent, but don't forget, you have to take one image for 1 point. So you project this laser line into space, it hits some surface, you see the corresponding point in the image, you take that image, you do the reconstruction based on triangulation, again, so the intersection of the laser line and the projection equation of the camera. And then you move the laser to a new point. Yeah, you scan the scene. For every new point, you need to take a new image. And innocent as that may sound, because an image, well, that is acquired in 20 milliseconds, 30 milliseconds maybe. Nonetheless, if you have to do that for thousands of points, and you have, then that becomes a real pain. Because don't forget, if you have 100 by 100 resolution, so say 10 points horizontally, 10 points vertically, well, that's 10,000. And 10,000 times 20 milliseconds, oh my God, that's already in the range of minutes. So it's getting just too long. We can't do that. So the whole thing is absolutely horribly slow if we do that. So that's why people very quickly went to a new technique. So, first of all, I want to also mention another problem, by the way. So time, being slow is certainly one problem, but actually there's also another. You have that situation, so you have that laser, it projects onto some surface, so it hits the surface, let's say, in this point. So here you will see this bright laser spot. You see here the image pretty well. So you have to take the projection line, intersect with the laser line, and where the intersection is, triangulation, is the point in 3D. All very nice and well. But here, of course, we have the same problem as what we had for stereo already. Namely, a little bit of noise on our equation of the laser line or the projection line in the camera, and whoops, you don't have an intersection at all, right? And guess what? That is, in fact, the normal situation. So, two lines in 3D intersecting is not really normal. Most pairs of 3D lines won't intersect. So, the chance of us having a problem is huge. Right? So we don't only have the problem of speed, we also have the problem of then not finding a real intersection. We saw with stereo, there is a way around it, algebraically and so on, but it's a bit of a hassle. And we can solve the two problems of speed and this problem of not finding an intersection with one solution. Okay, and that is placing here at the laser a cylindrical lens. What that cylindrical lens will do is to open up the line of light that the laser normally shines into a sheet. So rather than a line emanating from the laser plus the cylindrical lens will now shoot into space this sheet, planar sheet of light. And here you go. So that's now the situation. And what we get is that this sheet of light will intersect the surface, not in a point, but in an entire curve. And you see still that curve very well because it's very bright. It's a laser intersection with that surface there. So you see that bright light in the image plane, and for every point along that line you can draw the projection line. Like for instance for that point, you have the projection line here. You know the equation of that sheet of light, and where that line and that plane, where that sheet of light intersect, there is a 3D point. So now why is this solving all our worries? Well, kind of. First of all, this goes a lot faster than what we had before, because now we can reconstruct all the points along that line from a single image. Okay? We still have to scan, but we have to scan that plane just in one dimension. That laser line we have to scan in two. Now it's a single scan. And per scan, per sheet of light, so per image, we can have all these points along that curve in one go, basically. We don't have to take another image. We just have all those points from a single one. And then of course you have to move the sheet of light and take a new image. But the number of images we have to take is so much smaller than before. If we look at the previous case, easily thousands of images have to be taken. Yeah, maybe a couple of hundreds of images. So still not so good, but a lot better, a lot better. Secondly, we had this numerical problem before. We had a problem that if you try to triangulate, it won't work, because the line of the laser and the projection line of the camera will most probably not intersect. We're almost guaranteed they won't intersect. Here, we will have intersection, almost certainly, because this is a plane and a line, and a plane and a line in 3D normally have an intersection. So from something that would be normally not intersecting, we go to a situation where intersection is normal. So once we have an intersection, we have the point in 3D, and that's a very normal situation. So a plane and a line do normally intersect. Noise has little influence. Maybe the plane's a bit off, the line's a bit off, but still the intersection will still be pretty much where it had to be, and we find it without much ado. So also numerically, this is a far more stable thing to do. Here's an example. Suppose this is the object we want to scan in 3D, and this is our scanner. We have a camera. Our rabbit standing here. This is the image the camera sees, and actually we have also this projection unit shooting out that sheet of light that will intersect with the rabbit along a curve. That is quite easy to see in the image. It really stands out as a bright line. And now, if you want to have the 3D coordinates of a point along that line, we have to look at the intersection of the corresponding projection ray and the sheet of light. That point. Okay, and we can do that for all the points along that intersection. So for all these points here, we can find the 3D from a single image. We still have to scan. We still have to move up and down this sheet of light, rotating it. So here you go. But now it's a one-dimensional motion. It's much more easy and cheap to fabricate. You have far fewer images to take. And that generates a complete part of this object surface. Of course, if you want to have other sides of the object, you would have to move around or you have to turn around the object. But that's the same for many of the situations we saw, the method that we saw and will see, including stereo and all this. All right. So here is an example of such a sheet that has been reconstructed from a single side with such a line scanner. This type of scanner has known quite a bit of economic commercial success. And here you see different scanners that have been brought on the market that are based on these kind of line scanning principles. And you see you have there top left small tabletop model for small statuettes for small objects. And then top right somewhat bigger objects. And here you have this special chair, and the head is on top here for the scanning, so that will project lines again to do face scanning. And this is an entire body scanner. So these elements will project sheets of light and observe them, and then the whole thing moves down to do complete scanning of the person. And this is a bit also a disadvantage. For different sized objects, you have to build different hardware. As you can see, not all scanners can do all the objects that are on this slide. They are built for a certain working volume. That's a certain disadvantage for these scanners. Here's another tabletop model, same principle. Okay. Then we go to the next method, and that is structured light. And again, this is an active method. It is based on having a camera and a projector, and the projector will project a pattern. So we have modulation. That's why it's an active system. And it's multidirectional because we project and observe from two different points. Now, as we were saying, we went from line scanning, from point scanners, having these laser points, to entire lines, and that was speeding up the process quite a bit. But still, we had to take quite a few images. And there were moving parts, and that is always costly, and there will be wear and tear, and after a while the motion is not very precise, and then the 3D quality suffers from that as well, because your calibration is no longer okay. So can't we do without moving parts? Can't we do with just fewer projections? That's the idea here. So we'll project special patterns. And let me give an first example maybe rather than going through this. Okay, so suppose you have one projector and a camera. And the projector could be like your normal projector used during the courses, right? You can project any pattern. It's important that you can change the pattern that you project. But nothing moves, you just project this pattern. And this is the initial pattern that you project onto your scene. Half is black, half is white. And then of course you have a camera observing this. But the camera sees, oh, the point here is in the dark, or it's in the bright part of the pattern. And you have a code that you note correspondingly. So we have a 0 or we have a 1. But then we come with the second pattern. And gradually you see what these codes are for. They localize where you are in your patterns. Here's the second pattern. And again, it's in part black, in part white, but the subdivision is different now. We have a subdivision of the two halves that you had before, again into new halves. And depending on whether you see a dark part of the scene or a bright part, you remember a 0 or 1. So now in this case, you have twice 0. So the camera now sees twice its points falling into the dark region. And you keep on doing that. So here's the third pattern that you project. Again, a subdivision in half of all these bars that you had before. And same principle of coding. Now, again, here we are in the dark, but here we are now again the bright parts. So, and again, okay, and again. Now, what this is in the end about is identifying multiple projection planes. Think about the line scanner that we had before, the sheet of light. We had to know the equation of the sheet of light to do the triangulation. The same here. You have to know where exactly we are in this pattern. In fact, all these black-white and white-black transitions correspond to planes that are shot out into space. So if you know on which transition we are, we have the equation of the corresponding plane, and we can do the triangulation. So the code is telling us where we are in the pattern. Now, why these strange patterns? Well, it's much more economic to do this than what we had before. So here are again all the patterns that we have projected. We start with this coarse one and we end it with the final one. So in this case we only have 5 patterns. Now suppose with the line scanner, and by the way, for each of these patterns we took an image. So we have been taking 5 images. Now, if you think about the line scanner before with a sheet of laser light, for every position of that plane, we had to take an image. So here we take only 5. That would have allowed us with that laser line scanner to only look at 5 sheets of light. That would be a very crude reconstruction of our scene. Here we have identified far more than just 5 planes, because every transition can now be identified uniquely. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm looking at the lowest row here. All the black, white, black transitions define such a plane in the end, with a unique code, so we know exactly what the transitions we are looking at. So even if we are only projecting like 5 planes, de facto we are projecting many more of these virtual planes. So we can do triangulation for each and every one of them, and that from only 5 images. So this goes up in terms of number of planes much faster than the laser line scanner that we had. So if you have n patterns, we have 2 to the power n identifiable lines. Goes up pretty fast. Okay. So the number of projections and therefore the acquisition time is much lower than what we have for a laser line scanner. That's the take-home message of this thing. And now, of course, one can think, can't we push this a bit further? 2 to the power n. But what if we could increase the 2? We have 3 to the power n or 4. Well, one way of doing that would be if one were to project with colors. For instance, red, green, blue. Then we have 3 to the power n, because we can play the same trick. This is the first pattern, and that would be the second, and so on. So it goes up a lot faster than just with 2 to the power n. Now the problem is, this is all nice in principle, but there will be sometimes very strongly colored images, strongly colored objects in the scene, and then there may be interference of the colors of the object in the scene with the encoding. So that's why in practice people have not been using this too often. So the binary pattern, yes, this is maybe a little bit living dangerously already, because maybe we cannot get the code too precisely. If we have very strongly colored objects on which these colors appear, then we may make mistakes in which color region we actually are. So, not so practically useful. More useful is if we go to more complicated patterns. And in fact, this is another system that we did around 95, so quite a while ago. But this is a one-shot system. So it will project only a single pattern and take a single image and get the entire 3D, actually even the texture, from a single image. So that really reduces the acquisition time a lot. Here's an example of such a pattern. We have been using multiple. The highest resolution is not this one, but this gives a good example of what these patterns are about. And I have to draw the basic principle. So you see this kind of checkerboard being projected. It's the same principle as before. You have a projector from one side and then a single camera looking from another. Slightly different position. And we have this checkerboard of black and white patterns being projected. So that could be white, and this is white, and that's white, and that would be white, and this would be white. That kind of pattern makes it easier to find these transitions. These are actually the planes we will be looking at again. So one of these planes here is also pretty easily visible in that pattern because you have that checkable thing. But then we still have to encode which of the planes we are looking at. So we have now to include inside the pattern a code of where we are. And the principle here is that at the intersection there is a bit of information. So at the intersection of these different squares of the pattern, you have all these information bits. And they are white or black. So we project white or black. And you also see that a bit. If you look at the corners where the different squares, the bigger squares, touch each other, you have interruptions, white patterns or black patterns. And then we have here 6 codes in total, 6 code bits. 64 lines can be identified uniquely with this particular pattern. All kinds of special considerations were also applied to make sure that the reading of the underlying code could be done with sufficient robustness, by the way, but that would lead us too far. Anyway, it's all about extracting that basic pattern, then seeing what is the local code that identifies these planes from a single projection. So in these squares are 1 or 0, white or black. Okay. And that gives 32. There are 6 bits here, so that gives all the different codes for the different lines that we can encode. 64 in total. Alright, so pattern analysis, and that's the underlying 3D reconstruction now from that single image. 2 different views of the 3D reconstruction. And you see 2 things. First of all, the resolution is not so good, right? It's a little bit limited. 64 by 64 is not huge, and Some of the points, of course, are not even covered by the pattern too well, so the actual resolution on the face itself is even lower. And secondly, this is a 3D reconstruction, but you don't have the texture. And getting the texture is difficult with this particular pattern because you have all these black and white squares. So you can actually do better, as we will see in a second. This is a practical application of this, and that was for the 3D reconstruction of pigs. These animals are very nervous, so you can't measure them too well. They would constantly move, so they already feed them to calm them down a little bit. And then it's also important that your acquisition time is not long. You can't tell the pig, stand still, please. So it all has to happen in a very short acquisition time. That's why this one-shot technique, based on a single image, is so important for that application. So you would have the pig standing there and all the different images being taken, then a good image would be selected. From that image, the pattern is being extracted, and the 3D reconstruction is being made. So that's the detection of the pattern, and then you have the reconstruction of the surface in 3D. All right. So the one-shot nature, the very short acquisition time, is important here because the scene is moving, and we have not highlighted that too much. But every time you need some time to acquire means that not too much must have changed in the meantime. Right? So short acquisition times are not only important because you don't want to spend too long, but also because it allows to capture more dynamic scenes. Here's another system that we did, and that's a normal camera, and that is a normal flash, but in the flash is a slide, and the slide projects a pattern. This is a much finer pattern. It has been produced with lithographic technique, so it's much, much finer. Now we have hundreds by hundreds of lines. But again, this is a small code inside. Difficult to see, but it's a code. And that is being extracted. And these are some results for the top image. So one image is taken, and then the raster is extracted again in 3D. This is actually the texture read between the lines, literally, and mapped back onto the surface here. So this is surface, and this is now the textured surface from the same image. Of course, in the meantime, we are all used to one-shot techniques because a bit later, the Xbox, well, a bit 15 years later about, the Xbox did something similar, a one-shot active technique. This is the Xbox One. Xbox 2 uses a different principle. But Xbox One, or the Kinect One, I should say, it was actually based on a structured light technique, where a pattern was projected in the near infrared. So you can't see it, but actually the camera can. We have pointed it out before, that silicon is sensitive to the near infrared, even if the human eye is not. So if you don't filter it out, your camera will see the near infrared. That pattern is in the near infrared, so not visible to the user who's playing his game, as if nothing is happening, but in the meantime it's constantly being projected on with this pattern that is being analyzed, and from every single frame a 3D reconstruction is made. And what the Kinect also did as a part of impressive performance was also then in real time extracting the pose of the person playing the game. Here's a kind of pattern, all these fine dots, right? But you can't see them by eye. Here's a camera, a near infrared camera would see that. Because if you let the camera see the near infrared, that is indeed what you would actually see. So you have all these patterns being projected on the hand, gives you kind of a locally identifiable pattern that can then be used for the triangulation. Think a bit about the texture story we were telling when discussing stereo. It's a bit similar to that. You have all these unique patterns, and that tells you where in the projection pattern you are, so how to do the triangulation. We have been using that also for many other movies. So that's again back to our system with the handheld camera plus flash system that you saw before, and then actors could be actually scanned. This is for the movie XXX, for instance, but we have done several such movies. So these are some James Bond movies. There's Ice Slider Die Another Day. That was actually made in clay, scanned by our system, and then textured to make it look more fancy. And so that's the result that was used in the James Bond movie based on the scans we did with our system. This is a Lara Croft movie, Tomb Raider. So same principle, cheap model made, then scanned and then made to look real by texturing the 3D model. So that's a 3D construction made from the scans that we produce with this handheld camera thing, and that is the reconstruction. So that was an underwater scooter that Lara Croft was using in that movie. All right. So now the important thing of a one-shot system, I've been pointing it out before, is that the scene can move because the acquisition time is short. Of course, the scene cannot be too dynamic in comparison to the acquisition time. But if you have normal motion, normal video speeds will do. So if you project a pattern onto a dynamic scene, you take a video, seeing that pattern, and then for every single frame in the video you make a 3D reconstruction. You can then glue them all together again. You can get a kind of 4D movie, a 3D plus time movie. So that would be like the original performance. So, okay. And then from that, you can make all these 3D reconstructions and play. So now these are 3D reconstructions from the previous movie all put together, and yeah, a little bit of tricks were played to them. Okay, and this dynamic scene could be done indeed because the acquisition time is so short. This is a one-shot system. As we explained before, you have this complicated pattern being projected and analyzed. And again, a more commercial use. This is a scene we did from a movie, League of Extraordinary Gentlemen. And there is the Invisible Man in there. But of course, he was quite visible, so they had to use post-production to include that performance into the scene. I can't go into too much details what was going on exactly, but you see here the pattern being projected again, and then from that pattern you can make a 3D reconstruction of the action, and then part of that reconstruction would be used as so-called cream the Invisible Man would put on his face to become visible in the actual scene. Now here is something additionally going on. So in the previous video I was just showing frame by frame reconstruction all put together, and your brain would integrate everything into a single three-dimensional motion over time. Here we go really after the motion. A bit more like a Kinect and its action recognition. But of course this was several years before. More than 10. So that's the action that then finally went into that movie. And here you see the scene. Guy comes in, says his lines, and that's the reconstruction that is actually put into the scene separately. Okay, so the white thing is an additional add-on onto the scene. So you can do those dynamic things if you are just not spending too much time on the acquisition. One-shot techniques are key. Yeah, here's another technique. I won't spend too much time on it because it didn't really work, but it's an interesting idea. So again, in order to really minimize the number of projections, here is the basic idea. You have two patterns that you project one after the other. One is just an equal sheet of light, same intensity everywhere throughout, and then you would project that second pattern with a linear decrease of intensity, the increase of intensity from left to right. And then you can take a ratio. You have to linearize the response of your camera a bit. You have to know about that. But you can take the ratio of what you see here when that pattern is being projected over what you originally saw when that pattern was being projected. And that would then give you the column in this pattern where you are. And therefore, from two projections only, you get a 3D. But of course, this is very vulnerable. Response of cameras cannot be linearized that easily either. So this is very prone to noise in the end. I don't know of any real application of the thing. Different for this one though. Now, again, we are not really projecting a single pattern, it's not really one shot, but it's three patterns in very, very short succession. Here we have the projector, and in the projector, like any other normal projector, is this color wheel. And so it will project red, green, and blue. And then you have cameras. You have these two cameras here, these two high-speed cameras, and then the slower, 3 times slower camera in the middle. Why? Okay. So, the first thing that we did is to take out the color wheel from that projector. So now it would project the red, green, and blue patterns in very fast succession without being red, green, and blue. But that allowed us to project 3 patterns in very fast succession. So the 3 would be projected about 60 times per second for all 3, for the triplet. And what was the triplet like? So here are the patterns that we would project. Here are these sinusoidal patterns. So here you see 3 patterns. We call them IR, I, J, G, and IB for red, green, and blue. But of course, the color wheel is out, so there's no color involved at all here. Okay, but that's the red phase, the green phase, and the blue phase. We project a pure black and white pattern with intensities according to that trigonometric function on top and middle and the bottom. And the only difference between the 3 functions is that they are shifted by 120 degrees. Now, it's interesting that from observing the 3 intensities, you can determine where in the pattern you are. So you can, again, if you have a projector here and the cameras here, you can determine the column in those patterns where you are by comparing red, green, and blue, the 3 intensities. That's one thing. So you can identify this virtual projection plane, if you like, to do the triangulation. A second thing is, if you sum all 3, IR, IG, and IB, you just get a constant. And that's very interesting because we also want to measure the texture. So the slower camera, which integrates over all 3, gives you just the color image, the texture that we have to put back onto the scene if you don't want to only have 3D but also textured 3D surface. So here we have the 2 equations, right? So for the texture A, we just sum them up and divide by 3. And that is basically it. That is the color. And then phi tells you where you are in the pattern. A bit more complicated. Everything happens in real time here, and that's the difference with respect to our earlier one-shot systems. So this system would yield the 3D on top here, and then the texture, a bit difficult to see, on the bottom, all in real time. And then you can also steer a virtual phase. So on the left you have the system observing the phase that is acting there, and you see the 3D reconstruction being built at the very, very same time. And that 3D reconstruction generates that phase on the left, so it steers the phase or in this case the two faces. So a performance is copied to another face in real time and mimics the expressions of the real face. So this is all happening in real time. Okay, so again, this is a bit beyond 3D acquisition pure, because now part of the analysis is the expression and then transporting that expression onto a virtual face.